So, like I mentioned before, we are starting into a new chapter here. And this new chapter is chemical equilibrium. Now, to understand chemical equilibrium, I want us to go back to something that we were talking about yesterday. Yesterday, we made specific mention of mechanisms, and we talked about fast reversible step mechanisms. And we talked about the idea of a forward reaction rate and a reverse reaction rate, and instances where those two reaction rates would be equal to each other. Now, yesterday, we were using that calculation to substitute out intermediates in our rate laws to help us define the true rate law of the mechanism. Today, we're going to do largely the same thing, but instead of focusing on the concentration, we're going to be focusing on that composite of rate constants, those Ks. And that's going to lead us in a new direction here. So we will be in this unit for the next 3 days. And the primary direction for today is we're going to be looking primarily at these first 3 sections. Tomorrow, we will get into these 2 sections here where we start to do some calculations with equilibrium. And then Thursday's class is all about one particular technique. Chem 106 students know it well because it dominates their lives for the better part of a month and a half, and that is the ICE table. And we'll get more into what that is. Actually, we'll see it tomorrow for the first time. But what an ICE table is it's basically a mathematical way of organizing how a system changes as we go from I'm starting with just reactants to now I have a system at equilibrium. And how do I monitor how much everything has changed to get me to that equilibrium condition? So let's get into some of the finer points here. Let's start off with a definition. By definition, equilibrium is a state of balance in a system. Now, we're probably most familiar with static equilibrium, the idea of balance of position. So you and a friend are on a seesaw, and if there is proper weighting of the seesaw or positioning of the lever, you are basically sitting opposite each other and neither is up or down. You're in a state of rest. That is static equilibrium. There is no movement, there is no change of position. The system is in balance and it is at rest. But that's not what chemical equilibrium is. Chemical equilibrium is an example of something called dynamic equilibrium. To picture dynamic equilibrium, what I want you to think about is think about a person walking up a down escalator at such a speed that they are neither traveling up the escalator by going faster than the movement of those steps, or down the escalator by moving at a motion slower than the steps are forming. They are continuing to be in motion, yet they don't appear to be going anywhere. That is dynamic equilibrium. And most chemical systems proceed until they get to a state of dynamic equilibrium. Even the ones that we would talk about as going toward completion or that go to completion, the dynamic equilibrium still exists, but it rests far, 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 far toward the product side. And in the case of a reaction that's not reversible, that's exactly where it stays. So that's the term. Equilibrium that we are describing here is one of dynamic equilibrium. And what we want to kind of call back to is one of the reasons that we started with kinetics is kinetics established the idea of reaction rates, the idea that I can monitor a reaction and see that the reaction is proceeding at a certain speed. Well, one thing that we saw, regardless of the order of reaction, is that at some point the reaction basically stopped producing product. And what we describe in that case is we have a reaction where the forward reaction and the reverse reaction have equaled each other out. That's what equilibrium means as far as a chemical system is concerned. When a chemical reaction that is reversible starts, it will start pretty heavily in the forward direction because we just have reactants present. But once some of those reactants turn into products, if the process is reversible, then some of the products are going to react with each other to form reactants back again. And what we're going to see is that there's this kind of mirror image relationship between the rate of the forward reaction and the rate of the reverse reaction. Where the forward reaction is going to start off fast and get slower because the reactants are starting to run out, their concentrations are getting lower. And the reverse reaction is going to start off slow and get faster as more and more product becomes available to reverse back to. But at some point in the middle, what we will see is that the two reaction rates basically come together. And that's where we say equilibrium exists. The reaction is still ongoing. Reactants are turning into products, products are turning into reactants. But now the reaction rates are equal to each other. So visually speaking, we can't tell that anything is happening. Now, the question you might have for me then is, well, how do we know that the reactions are continuing if we don't see a difference? And the answer to that is we can monitor the system and we can also influence its environment, change its temperature, change its pressure, change something about it, and the reaction will kick up in one direction or another again. And that's how we know it's dynamic. Because if it was static, if it stopped as soon as we hit the equilibrium mark, think about it from an activation energy standpoint. We have to overcome activation energy again to get it to go in either direction. But because it is continuing to go on and on and on and on, it's in this infinite state of flux, back and forth, back and forth, back and forth. And all we have to do is change the environment and we'll see it go one direction or another. Similarly speaking, take, for example, a cup of water. Now, a cup of water will evaporate over time. That is just the nature of vapor pressure. Now, if I keep that cup lidded, we will eventually hit a vapor equilibrium state inside of the cup where the water is evaporating, but also vapor molecules are going back into the liquid. And the liquid level inside the cup would eventually stop changing. But all we would have to do is, if we remove the lid from the cup, and now there is no longer a set vapor pressure, we're now talking about the pressure of the room around it, and the vapor is free to move throughout the room. Evaporation is going to continue to go in the forward direction toward vaporization because there's far less water vapor in this room than there is right above the liquid itself. That's dynamic equilibrium. Again, that's how we know it's dynamic, because if it wasn't dynamic, then we would see we wouldn't see the reaction immediately start up again as soon as we removed whatever it was that was keeping it at equilibrium. Whether it was the temperature condition, concentration of the reactants, pressure, whatever. So what do we do? How do we talk about equilibrium? What do we care about? Well, I want you to consider this reaction here. And moreover, what I want you to consider is, if we break this reaction down like we did yesterday, where we've got K1 for the forward reaction, K -1 for the reverse reaction. If I was going to look at the rate for the forward reaction, it would be equal to the rate constant K1 multiplied by A to the 8th power multiplied by B to the bth power. Because again, if we think about this mechanistically, the stoichiometry of the elementary step is the rate law. And if I look at the reverse reaction, K to the K -1 times C to the cth power, D to the dth power. What we did yesterday is we recognized, okay, R1 and R-1, those are equal to each other. So we set these equal to each other. So K1 times A to the 8th times B to the bth is equal to K -1 times C to the cth and D to the dth. If we take these, and instead of solving for C or D like we did yesterday, if we put all of the K components on one side and all of the concentrations on the other, so I'm going to divide each side here by K -1 and by A to the 8th and B to the bth. Then my K -1s cancel on this side. My A's and B's cancel on this side. I get K1 over K -1 is equal to C to the cth over, or times D to the dth over A to the 8th and B to the bth. And If I take this composite of rate constants and rebrand it with a capital K now instead of a lowercase k, we have the expression here that was given on the slide. And that's basically what equilibrium constants are. Equilibrium constants are, if you want to think about the reversible reaction, they are relative ratios of rate constants. And we can calculate them not by using the rate constants themselves, but by using the concentrations of the chemical species in the reaction equation, which is a lot easier to do. You all know, because you've now done the experiments, getting rate constants and calculating rate laws from experimental data is a time-consuming process. But if I can avoid all of that and just focus on what is the concentration of the reactants and what is the concentration of the products, that in so many ways can be such an easier endeavor than having to experimentally go through and do 20-minute long reactions where we're monitoring coloration over time and then taking the data and interpreting it and then figuring out what the interpreted data means and all of that stuff. And so when it comes to equilibrium constant, this is what we're ultimately doing. Now, what you're going to see, first of all, I got to point out, equilibrium constants are capital K variables. Rate constants that we saw for the first part of this class were lowercase k. There is a difference. You want to make sure that you are specific in your writing out of your k's in terms of what you mean. My wife's a chemistry teacher as well. She told me that she has her students use lowercase cursive k's for rate constants just as an additional kind of way to tell one from the other so that they don't look so similar. However you want to do it, just make sure that there is a difference. Second thing that you're going to see a lot with equilibrium constants is the use of subscripts. Subscripts on the K usually give us some kind of insight about what the K is describing. So when you see K sub C like this, that means that this is an equilibrium constant with regard to concentration. That's what the C stands for. We will see as we go through this equilibrium unit that there are going to be other subscripts that are used. We'll talk about another one today, P for pressure. We use that one for gas phase in particular. But at the end of this week, we'll also talk about A's and B's for acids and bases, along with a whole bunch of other things. One thing that you can safely assume, if you see a capital K with no subscript, it's generally safe to assume that it is referring to K sub C here. By default, concentration is usually the way that we will regard most calculations of K. Again, really the only time we see Kp is if we're dealing with gas phase kinds of reactions, because that deals with pressure, and pressure is a gas phenomenon. Now, some things to know about Kc in particular. Kc is a reference to an equilibrium constant with concentration. Now, in order to use it, we have to have concentrations for the substances in question. And that's going to limit us because we really can only talk about concentration for two phases. The gas phase, which we can talk about that in terms of pressure as well, but we can also talk about in terms of concentration, moles per liter, and the aqueous phase, where molarity is already a pretty well-known unit to us. Pure liquids and pure solids are excluded from the matter, and the reason they are excluded from matter is because pure liquids and solids, while we might be able to monitor a concentration for them per se, their concentrations do not change because they are pure substances. Concentration of water is 55.6 molar. It's always 55.6 molar. It doesn't change. And so since it doesn't change, it really doesn't belong in the equilibrium expression, because ultimately in the equilibrium expression, we need the ability for those concentrations to change as the reaction changes. As we go from reactant to product, the concentration of those things has to go up or has to go down. In the case of pure water, it's not going to. Same thing if I'm doing something with solid phase nickel. The concentration of nickel based on its density is not going to change. Now, the amount of nickel might change, but since we're dealing with concentration, the concentration of a pure solid is not going to change because its density is not going to change. And so for those reasons, pure solids, pure liquids, we leave them out of that equilibrium expression. We only focus on the things where we have concentrations, where the concentration is a value that changes. So that leaves us with aqueous solutions and gases. Like I mentioned before, there are other versions of the equilibrium constant besides Kc. The subscript that is attached to them usually tells you something about the equilibrium that is being discovered, or that we're looking at in particular. The first of these that we will explore is Kp. Kp, where P is in the form of pressure, where we find this useful is in gas phase reactions. And what we will notice is that if the reaction is gas phase, we will use pressures instead of concentrations. Now, if we have a reaction that is mixed phases, the Kp for that experiment, Kp for that equilibrium expression, would only focus on the gaseous parts of the equilibrium. So in this scenario, let's just say that B and D were both gases, but E and A were not. In that particular case, then we would leave E and A out of the expression, because since they're not gases, they would not exhibit pressure. If we know Kc or Kp, we can interconvert between them. The calculation, the equation for that looks like this. The value of Kp is equal to the value of Kc multiplied by the universal gas constant R and T raised to the power of delta N, where delta N is the number of gas molecules as products minus the number of gas molecules as reactants. Now, an important note about the value of R and the value of T here. Since we were talking about gases, we want to use one of the gas phase universal gas constants. So yesterday we talked about 8.314 as a unit of R because we were talking about energy. Here we're back to a more traditional kind of universal gas constant. And for temperature, just like we would in the ideal gas law, temperature has to be in Kelvin. But that delta N value does tell you a lot of important information. For one, if we have equal amounts of gas on both sides of the equation, well, delta N in that case is 0, which means RT to the 0th power would be 1. Kp and Kc are identical to each other in that scenario. Otherwise, we're going to see an impact on Kp that will be making it larger if there's more gas on the product side than the reactant side, or smaller if there are more gaseous reactants than products, because that's going to be based on whether delta N is a positive value and we multiply, or if it's a negative value and we divide. All right, any questions so far? All right, let's take a look at a practice problem then. Okay, first thing that we want to do, we want to determine an equilibrium expression for this reaction. And then we want to calculate the value of Kc and Kp at 25 degrees Celsius if those are the equilibrium concentrations. So the first part, to determine the equilibrium expression, we're going to start with capital K, and it's equal to the concentration of the products over the concentration of the reactants. Well, the product here is carbonyl chloride, CoCl2, and it's raised to the first power because the coefficient here is 1. And the reactants, I've got carbon monoxide also to the first power, and I've got chlorine also to the first power. And so that would be my equilibrium expression here. Concentration of the product divided by the concentrations of the reactants. Since none of the reaction species are solids and none of them are liquids, everything gets included here. So that would be the value of Kc. Now, if I were doing Kp, it would be the same thing, only with partial pressures. The pressure of carbonyl chloride to the first divided by the pressure of carbon monoxide multiplied by the pressure of chlorine. Exact same fundamental idea, just using pressures instead of concentrations. Again, since they're all gases, they all get included in the Kp expression. But now let's answer that question here at the bottom. What is the value of Kc and Kp at 25 degrees Celsius? If we have those values, okay, well, for Kc, it would be the concentration of the carbonyl chloride, 1.47 times 10 to the negative second, and that is raised to the first power, divided by 1.8 times 10 to the negative sixth, to the first power and 1.8 times 10 to the negative sixth also to the first power. Something really important to know. You'll notice that even though I was given units for the molarity, I did not include them in the expression here. The reason why is relatively simple. Equilibrium constants are not given units. Even though we make them with stuff that has units, we consider them to be a unitless measurement. So you don't need to bog yourself down in the, well, this would be molar to the negative first or molar to the negative second or atmospheres to the third or whatever. If we're giving you an equilibrium constant, it's going to be unitless because there is more important information to glean from that. The unit itself is kind of useless. Doesn't tell us much of anything. 1.47 times 10 to the negative second divided by 1.8 times 10 to the negative sixth divided by 1.8 times 10 to the negative sixth to two significant figures because we only have two in our initial concentrations, 369, 4.5 times 10 to the ninth would be the value of Kc for this expression. So that's the value of Kc. Now for Kp, Kp is equal to Kc times RT to the delta N. Well, we know Kc. Kc is 4.5 times 10 to the ninth. Let's talk about delta N. N for the products minus N for the reactants. We have one product gas molecule and two reactant gas molecules. So this is -1. So we're multiplying 0.0821 times 25 Celsius is 298 Kelvin to the negative first power. If you remember from algebra, negative exponents requires to just flip them, take the reciprocal. So we can think of this expression as 4.5 times 10 to the ninth divided by 0.0821 and 298. Any way you do it, we get 1.8 times 10 to the eighth. So because there were more gas molecules on the reactant side, our Kp value is smaller than our Kc value. And that's how it is most of the time. Unless we are just dealing with extremely cold kinds of conditions, the combination of R and T, you multiply them together, you're going to get a number greater than 1. Again, unless you're at like 40 Kelvin or something like that, or 4 Kelvin. So unless you're at an extremely low condition, R and T is going to be greater than 1. And so the exponent is going to tell you, does the value go up or does the value go down? And in this case, because there are more reactants, that value is going to go down. All right, any questions? All right, try this one then for yourselves. Calculate the value of Kc given this equilibrium expression and the value of Kp given in the problem. So you're going to have to do a little bit of algebra here because we've got the expression this way. Oh, sorry. We've got the expression that way. Now we got to solve for Kc instead of Kp. Okay, so the key to this problem is we've got to start with delta n. And so this time around, we see that we have 3 product, 2 from the nitrogen monoxide, 1 from the chlorine, and we have 2 reactants in the NOCl. So delta n is equal to positive 1. And so the expression Kp is equal to Kc times RT would be the result. Now again, this time we have Kp, we're trying to solve for Kc. So before I put any numbers in, I'm going to go ahead and do my algebra with variables. And so I'm looking for Kp over RT to find Kc. Kp was 0.067. R is 0.0821. And we're at 500 Kelvin. So to 2 significant figures, 0.067 times 0.08, or excuse me, 0.067 divided by 0.0821 and divided by 500, we're getting 1.6 times 10 to the negative third. And so, again, the difference here, we talked about it. Since delta n was positive 1, Kp is going to be larger than Kc. Now, if you'd put in 0.0016, it would still accept it. All right, let's take a break right here. This is a reasonable stopping point for the first day. When we come back at 10 o'clock, we're going to talk about kind of what K means based upon its value, and we'll also get into some ways of manipulating K. So let's come back in 10 minutes.